Hello, my dear students. So in the last class, we have seen the definition of eigenvalue and eigenvector. So simply we will recall it. So whenever we are having a n-dimensional real vector space and a linear map from V to V, then alpha belonging to R is said to be an eigenvalue of T if we are able to find a non-zero vector in V such that T of V is equal to alpha V, and that non-zero vector is called as eigenvector. Remember that eigenvector is always non-zero. Next thing is, we have also seen that if alpha is an eigenvalue and the corresponding eigenvector is V, then for a non-zero scalar k, kv is also an eigenvector corresponding to the eigenvalue alpha. This we have seen last time, and we have also seen the definition of eigenspace. Basically, eigenspace is nothing but what? It is the collection of you can say all the eigenvectors of the eigenvalue lambda uh, together with the zero vector as well, naturally, which is not the eigenvector, right? Because we always whenever we say about eigenvector, we think that it is a non-zero one. So eigenspace is nothing but it is a collection of all those vectors that satisfies T of V is equal to lambda V, and naturally we can see that it is exactly the definition of eigenvalue and eigenvector. And now we are going to see the definition of eigenvalue and eigenvector only, but this time around for a matrix. So I will say over here definition, I'll say let A be a matrix of order n, means obviously we want a square matrix when we talk about eigenvalue and eigenvector. Then alpha is said to be an eigenvalue of A if there exists x not equal to 0 belonging to r raised to n such that ax is equal to alpha x. So try to understand the difference between the definition in terms of a linear transformation and in terms of a matrix. There is a slight change. Whenever you talk about a matrix, then this vector is from r raised to n naturally. And why r raised to n? Because order of the matrix is n. If the order of the matrix is 3, then this eigenvector will be from r raised to 3. And remember, it is a column vector, okay, satisfying ax is equal to alpha x. And whenever we talk about a linear transformation, it is this vector is from a vector space V actually, and that is nothing but T of V. The condition is actually the T of V is equal to alpha V, right? So now we are going to go for a theorem over here. Yes, so a vector space is given to us of dimension n, and T from V to V is a linear transformation, and they are asking us to prove that the following statements are equivalent. The first statement is alpha belonging to R is an eigenvalue of T. The next one is alpha I, not alpha, actually it is lambda, right? So lambda I minus T is not injective, where this I is identity map. The third one is lambda is an eigenvalue of a matrix A, where A is a matrix associated with T with respect to any basis of V. And the fourth one is lambda is a root of characteristic polynomial of A. And the fifth one is the system of linear equations lambda I minus A outside the bracket x is equal to 0 has non-zero solution for x belonging to r raised to n, has a non-zero solution x belonging to r raised to n. Now all these statements are equivalent, means if one statement is true, then other 4 becomes true, right? So how we are going to proceed with the proof? I will prove 1 implies 2, then we will go for 2 implies 3, then 3 implies 4, then 4 implies 5, and 5 implies 1. Okay, so first of all I will assume that lambda belonging to R is an eigenvalue of T, and we are going to prove that lambda I minus T is not injective. Now in order to prove that lambda I minus T is not injective, I am going to take the help of a famous theorem that we have already seen. So which is that theorem? if we are having a linear map from T V to W, this is a linear map. Yes, if T from V to W is a linear map, then you might remember then T is 1 1. 1 1 means injective only if and only if kernel of T is equal to singleton 0, naturally 0 of V. So now we are going to take the help of contrapositive of this statement. So what will be contrapositive? So kernel of T is not equal to 0 if and only if T is not injective, isn't it? So but remember T should be a linear map. So over here we are going to show that this kernel of lambda I minus T, in order to show that this lambda I minus T is not injective, we are going to show that the kernel of lambda I minus T is not equal to singleton 0. I mean it is non-zero, non-zero in the sense it is not trivial, means it is going to contain some non-zero vector. Okay, in order to show kernel of lambda I minus T, and right here, in order to show kernel of lambda I minus T is not equal to 0, we have to show that this kernel contains one non-zero vector. Is that okay? So let us begin that. So first of all I will say that let lambda be an eigenvalue of T. Okay, once I assume this, then what it will imply, since lambda is an eigenvalue of T, therefore we can say there will exist some V not equal to 0 belonging to V such that T of lambda will be equal to what? Sorry, T of V will be equal to what? Lambda multiplied by V. This will happen. Now we have to move towards kernel of T minus lambda I minus T. So what will be kernel of lambda I minus T? If you think of this definition, see our map is from V to V only in this case. So it will be the collection of set of all V belonging to V such that T of V is equal to 0 नाही येणार, कारण की आपण कुणाबद्दल बोलतोय, we are not talking about kernel of T, we are talking about kernel of lambda I minus T. So lambda I minus T of V should be equal to what? 0, isn't it? This is nothing but definition of kernel of lambda I minus T. So let us do it then. Remember this I is nothing but what? This is the identity map. So we have to show that this set contains at least one non-zero vector, and which will be that vector? That vector will be what? Our eigenvector, this one, right? So now since this is happening, so what can I say? I can say that this lambda V minus TV is equal to 0. Is that fine? This is simple algebraic calculations. Now since I is identity map, how can I write it? This can be written as lambda IV. Since I is identity map, IV will be equal to V, right? Minus TV will be equal to 0. Therefore, once I take that V out, what I'll get? Lambda I minus T outside the bracket V is equal to 0. So you can see that this condition is satisfied by which vector? This vector, and therefore V will belong to what? Kernel of lambda I minus T. Now since V belongs to kernel of lambda I minus T, therefore we can say that therefore this kernel of lambda I minus T is not equal to 0, and therefore by using this theorem I can directly say that lambda I minus T is not injective. But the question is lambda I minus T a linear transformation? Then we can use this theorem, right? And that is very easy. It is a linear transformation, because whenever you are having T1 and T2 to be linear transformation, remember the linear combination is always a linear transformation. I mean alpha 1 T1 plus alpha 2 T2 will be a linear combination only, where this alpha 1 and alpha 2 are some constants, some real constants you can say. Okay, so therefore this lambda I minus T is a linear transformation also, and since this is happening, we can say that lambda I minus T is not injective. So let us see the proof in detail. So I have assumed that lambda belonging to R is an eigenvalue of T. We have to prove this. Lambda I minus T is not injective. It is clear that lambda I minus T is a linear transformation. As I have told you, whenever you are having linear transformations, the linear combination is a linear transformation. So directly I will say as this lambda is an eigenvalue of t. Note that we have to show this. Okay, so as lambda is an eigenvalue of t, so there will exist v not equal to 0 belonging to v satisfying this property t of v is equal to lambda v, as I told you, and by doing some algebraic calculations you will get this. Yes, so some steps are skipped over here, but that is understood. So directly this step is written, and therefore this v will belong where to kernel of lambda I minus t, but this v is non-zero as it is an eigenvector. Therefore this kernel of lambda I minus t is not equal to singleton 0, and therefore lambda I minus t is not injective. Now we have to prove 2 implies 3. So just let us see what is 2. In 2 we have to assume that lambda I minus t is not injective, where I is the identity map, and we have to prove that lambda is an eigenvalue of A, where A is a matrix associated with T with respect to any basis of V. So this is the important thing to note. We have to prove that lambda is eigenvalue of A, where what is matrix A? It is a matrix associated with T with respect to any basis B of V, any basis of V actually. So the thing is, whenever you are having a linear transformation, I have already told you, you can always find the matrix representation of T, provided you should have a basis actually. So the same thing is over here. This A is nothing but what? It is a matrix representation of T, but no, with respect to any basis of V. Okay, not only a certain fixed basis, but with respect to any basis. Okay, that is important. So I will assume that this lambda I minus t is not injective. We are going to follow the same path of the previous part. Since it is not injective, I can say that kernel of this lambda I minus t will not be equal to singleton 0, since the result was if and only if, obviously, and this will imply that there will exist some x not equal to 0 belonging to what? Kernel of lambda I minus t, and this will imply that lambda I minus t outside the bracket x is equal to 0, and this will imply that lambda I x minus tx is equal to 0, and this will imply that tx is equal to lambda x. Is that okay? Because I is the identity map, so ix is going to be x again, and since this is happening where T is a linear transformation, this is also going to hold for the matrix representation of T, and I am going to use this notation for that. So it implies that this is nothing but what actually? This is the matrix representation of T with respect to any basis of V. So this matrix is also going to satisfy this one. Is that okay? Simply T is replaced by what? This, the matrix representation of T. Since the linear transformation is satisfying this, so the matrix representation of T with respect to any basis is also going to satisfy that. Okay, and I am going to call this as A, and therefore we will get Ax is equal to lambda x, and this will imply that this lambda is an eigenvalue of A, where this A is a matrix associated with T with respect to any basis of V. So let us go through the proof. Here you can see, suppose this is not injective, we have to prove this. So this kernel will be non-zero, so we will have some non-zero vector in kernel, it will imply this, it is by the definition of the kernel, we will have this, then we will have this T of x is equal to lambda x, and therefore for any basis this is going to satisfy, and I am going to call it as A, and this will happen now since x is non-zero. So therefore lambda will be an eigenvalue of A, and where A is a matrix associated with T with respect to any basis of V. Now we are going to go for 3 implies 4, where we are going to assume this, that lambda is an eigenvalue of A, where A is a matrix associated with T with respect to any basis of V, and we will prove that lambda is a root of characteristic polynomial of A, and this is very interesting to prove. Yes, so I have supposed that lambda is an eigenvalue of A, where A is a matrix with respect to matrix associated with T with respect to any basis. So we have to prove that lambda is the root of characteristic polynomial of A. So as lambda is an eigenvalue of A, therefore what will happen? So as lambda is an eigenvalue, so therefore this there will exist some x non-zero belonging to r raised to n. This is by definition only, such that your Ax will be equal to lambda x. So what it will imply? So this will give us Ax is equal to lambda I x, where I is the identity matrix, right? Just I have introduced that I. This will imply Ax minus lambda I x will be equal to 0. This will imply A minus lambda I outside the bracket x is equal to 0, and x is non-zero. Just note this. So if you observe it properly, this is nothing but a system. Actually it is a homogeneous system. If you recall, Ax is equal to 0 is nothing but what? A homogeneous system where A is a matrix of coefficients and x is a matrix of unknowns. So same thing we are getting here. So this is a homogeneous system of linear equations with a non-zero solution. Since x is non-zero, x is nothing but the eigenvector of A, and that eigenvector is satisfying this system, means this system is having a non-zero solution. So since this system is having a non-zero solution, what can you say about the determinant of the coefficient matrix? We have already seen this before. If the determinant of the coefficient matrix is non-zero, then the system will have a trivial solution, that is a zero solution. But that is not the case. Since this system is having a non-zero solution, so determinant of this coefficient matrix should be what? 0 only. So this will imply that determinant of this A minus lambda I should be equal to 0. And what does it imply? This implies that lambda is a root of characteristic polynomial of A, and that is what we wanted to prove. Let us go through the proof. So you can see this will happen. So this will happen. Yeah. So yeah, has a non-trivial solution. Therefore, this will happen. Non-zero and non-trivial is one and the same. Okay. Since it has a non-zero solution, any linear combination of that is going to be a solution. Okay. So therefore, has a non-trivial solution, and therefore this determinant is 0, and therefore lambda is the root of characteristic polynomial of A. Now we are going to go for the next part. So now I am going to assume that lambda is a root of characteristic polynomial of A, and we are going to prove that the system of linear equations lambda I minus A outside the bracket x is equal to 0 has a non-zero solution. Now we will assume that the system of homogeneous linear equation lambda I minus A x is equal to 0 as a non-zero solution, and we are going to prove that lambda is the eigenvalue of t. Now since this system has a non-zero solution, what does it mean? It means that we will be able to find some non-zero vector belonging to r raised to n such that that vector is going to satisfy this system, right? This will imply that lambda Ix minus Ax will be equal to 0. This will imply that lambda of Ix minus, now what is A? Remember, A is nothing but what? It is the matrix obtained by what? Somewhat like this, right? It was the matrix associated with T with respect to any basis. So just I have used that value, and this will imply lambda IV minus T of V is equal to 0. Now this is a key step over here. I have replaced this matrix by what? Now a linear transformation, and this vector x is replaced by what? A vector small v. But remember, this small v is from the vector space V, and this x was from r raised to n. So how is this v obtained actually? Okay, So since we have replaced matrix with a linear transformation, so naturally this vector has to shift from r raised to n to the vector space, because we know T is a map from what, V to V. So therefore we should have a element of V over here. So how we have obtained it? Just an example. Suppose I will take a case of R3. Suppose our vector is 1 2 3, then what I have done is, and suppose my basis has some vectors, let me say you can take any, but I will go for standard 1 0 0 0 1 0 and 0 0 1. Okay, suppose this is a basis of R3, then what I have done, simply multiply first vector by 1 1 0 0, second vector by 2 0 1 0, and third vector by what, 0 0 1. So that is going to give you the element of the vector space. In this case you get the same vector, that is 1 2 3, but depending upon the basis it may change. Okay, I hope you are getting it. Suppose we take some other basis of r raised to 3, then you can easily see that you will not get the same vector, the vector may be different. Okay, and that is this vector. Okay, now since we got this, now from here it is easy. So this will imply that T of V is equal to, now this IV will be what, it will be just V, because I is the identity map. And if you want we can do this in the previous step only, Ix च्या ऐवजी directly आपण इथे x लिहू शकतो, because I is the identity map, and over here we will have V only, and therefore T of V will be equal to what, lambda V, and this will imply that this lambda is a eigenvalue of T, and the corresponding eigenvector is V. Let us go with the proof. So therefore this will happen, and therefore this will happen. If you want just a change, since I is identity map x, since it is identity matrix, Ix will be x, and over here I will directly write it, just avoiding the complications. So V, and you can directly say TV is equal to lambda V, no need of this step. Yeah, and that is what we wanted to prove, and that's about this theorem.